And I was hoping to take you on a journey in my own career. Back in 2007, I got a dream job with National Grid in a particular team, and that team's job was to forecast with power, which in 2007 that was really new thing. And I'm hoping to take you on the journey of what we learned and when we learned it, how we learned it. So that's kind of one aim I have. The other thought is that, well, I'm a bit loud. Right, fair enough, I'll just carry on. The second thing I want to really journey with is how we had to adapt some of our processes as we went along. Changing an organisation is quite a challenging, difficult thing, especially if you're in a very large company like National Grid. And there's a lot of inertia where processes and ways of doing things that have been done for 20 years, people naturally want to carry on doing it the same way. But sometimes something like this comes along, means it has to change. So consider that as we go through these slides. The third thing to mention, really, as I describe this journey of wind power, think about the same journey for storage. Are there things that we learned about wind power and how wind power develops that are similar to how storage systems are developed? So have those three things in your mind as we go through. So I think that will right. So a few basics to start with. When we started wind power, we didn't really know a lot about it right at the beginning, and it's totally obvious, as we all know, more power, more wind, more power. And this is a tool I've used to educate people over the years, and it's pretty good. It's a simulator. You can search on Google, and you can select the wind speed, and it will tell you the wind power. And this will tell you what you probably already know. I'm sure most people in the room know how wind turbines broadly operate. So you go up to 4 meters per second, start getting power. 10 meters per second, it increases through a cubed law with the wind speed, and producing full power at about 16 meters per second, approximately. Different turbines produce power at different levels, of course. There are different designs. In the early days, the revelation that really we discovered to our horror was that at this speed, 25 meters per second or 55 miles an hour, wind turbines shut themselves down for safety reasons. So that caused a lot of problems. Still does cause us some issues because it makes it very difficult to predict what wind turbines are going to do at that wind speed. So how do we go about predicting wind power outputs? That's really the question and the journey. So the very first thing we started to do was to build a power curve. Plot a chart with wind speed on one axis and power outputs on the other, and you get a curve. I've got the curve. This is a very approximate curve, and you can see it's pretty straightforward. And we started very, very early days in 2006 and 2007 by just pretending that there was one virtual wind turbine in the middle of the country and the size of the capacity that we knew about of wind turbines across the country at that time, and found the average wind speed forecasted and then fed it into a very rudimentary model. And it was a bit crude. It gave an answer. Clearly we could do a lot better. So we decided to look at the different sources of information that we needed to do a better forecast. And one of the key things that's vital is knowing where all the farms are. And thankfully, there's some great sources of information out there on the internet. Renewable UK and DEC have a website as well. Databases of where all wind farms are located, how much capacity they have, all that kind of information. Really good. But we had to make sure that was good quality information. So we spent a lot of time, I spent a lot of time, cross-referencing these multiple databases to try and get the truth, or as near to the truth as I could find. So that was a challenge. So with storage in mind, as I mentioned earlier, interested to know if there's a central record of all storage systems installed in Great Britain that anyone has to sign. Hold that thought. Right, let's carry on. Another thing that we learnt, I started to learn a bit about fluid dynamics. I'm an engineer by training, but fluid dynamics scared me slightly. But the general gist of it is pretty straightforward. You wouldn't put a wind turbine in urban environments. The buildings interrupt the wind. Of course they do. It's pretty obvious, really. So a much better wind resource offshore. So in the early days, we started to see that trend where many, in 2008 and 9, the majority of wind farms were onshore, but there was the round 2 and round 3 offshore tenders happening at that stage. We saw the future would be offshore, and current numbers show the majority of wind farms are now offshore across the Great Britain. Right, this is an example of some of the early analysis that we did for various wind farms. We looked at the power output on the vertical axis and the wind speed on the horizontal axis. We just wanted to learn what was going on. And we saw various interesting things, like these pictures here. Strange lines across there. Wondered what they were, and started to twig. Actually, these are times where there's a few turbines that are shut down in these wind farms. This particular example, I remember this wind farm was increasing its capacity. It built 50% of its site, and 50% was operating. And through later months, the site became fully operational. So you can see the 2 stages of this particular wind farm. So we saw these things develop over the years. Very, very interesting. So we also started, myself and 2 other colleagues in our small team, we looked at meteorology, learned a lot about meteorology and about weather systems and how they move across the country and how they can be predicted and the effect that they have. So this is a low pressure weather system where wind speeds circulate around the centre of low pressure, and this system itself moves across the UK, blown across usually by jet stream. And the effect it has on power output, this is kind of an indicative chart, that the leading edge of the system increases with power output, as you would expect, with higher winds at the leading edge, and then the eye of the storm is much calmer, so you get a reduction in wind power output, and then the trailing edge catches the wind farms, and then that increases wind power again. So we see this pattern as storms move across. We wanted to really get our heads around error in our forecasts. What's driving the errors? We wanted to push those errors down as far as possible. So this is a chart my colleague David S. at the time, he drew up this to indicate roughly what are the big drivers of the error. Roughly the size of each box indicates the broad influence that each aspect has. So most of the error was driven by the weather. So on the early days of wind power forecasting, we started by looking at 3 sources of weather forecast data. We wanted to start off cheaply as we could, but we rapidly came to the conclusion it's
much better to set up a contract and get a proper weather provider. We approached several companies at that time, and now we receive very detailed forecasts of wind speed in various locations from lessons. But there's also local effects that at the early stages we were kind of ignoring, but the effects that we talked about just earlier, buildings and mountains and other features, drive the influence the wind as it flows across the terrain. So we needed to take them into account as well. And then the model itself, we started off with a single generic model and pretended that every wind farm operated exactly the same way, and that was good enough in the early stages. But then we thought we could do better. We started tailoring our models to individual wind farms, and that helped us in that area. We also looked at other things broadly. What else could it be? And air quality or air density. We had a thought that if the wind is blowing from the Atlantic, it has lots of moisture in it and is more dense, and therefore for a given wind speed has more energy to give to the wind turbine. And if the wind was blowing from a different direction, drier air might have a different effect. We did have a look at that, but found the effect was really minor. So we still ignore that effect at the moment. We may in the future take it into account, but there are bigger fish to fry. This gives you an idea just across the United States. Storm tracks, the different coloured lines are tracks of storms. Just gives you an idea of the variability of where storms will go. Because, as I said, the weather error has many aspects to it. Not only the intensity of the storm and the wind speeds that it brings, but the direction of it, and the jet stream and the weather systems around it can influence the path that storm takes. So there's a predicted path, and then there's the real path. And they may be different. It's quite a challenge for us to really get our heads around that. So, as well as doing all that work, we looked at some wind farms more specifically. So, Whiteley at the time, and still is a very large wind farm, fleet of wind farms. This overhead view illustrates the layout of Whiteley as it was. Each of these blue dots is a wind turbine. And just to give you an idea of the scale of this, if you haven't visited Whiteley yourself, it's worth looking at. It's about 10 miles across, and this is Whiteley Phase 1. Phase 2 is off to the right here. And just to put it in perspective, this grey area in the distance, that's Glasgow. So, wind farms are massive. So they're in all shapes and sizes, as you can see. Teal, very different layout. When we did some analysis on the data, we wondered why is the data so strange, and the truth is it's because it's laid out in this way, which makes perfect sense when you look at the prevailing wind direction. The prevailing wind would be blowing out from the screen across the wind farm as it's laid out. Very sensible, catches the most energy that way. And of course, if the wind blows across the axis of the wind farm, each of the turbines steals wind from each other, and you get a shadow effect. And that's something else we have to take into account to improve our forecasts. So, let me I'll just show you better. A picture speaks 1,000 words. This is one of our early forecasts. So this is what would be printed off and handed to the control room in the early days. You can see the date, 2008, and you can see the overall output forecast, this dark blue line, and you can see individual wind farms at that time. Just to put it in perspective, the total capacity that we were forecasting for was 1.2 gigawatts of wind farms on the DB system. And at that time, that was considered to be a huge amount. That's time to change. So, also we forecasted 3 days ahead, or current day, day plus 1 and day plus 2. And we forecasted for particular points in time. We did have the capability at that stage to forecast every hour of the day, but for this printout, for the control engineers, my colleagues in the control room, we only presented these particular times of day because they coincide with turning points of our demand, and they were key moments of the day that we were interested in. So even at that stage, we were considering how do we manage the information overload, how do we present just the information that's needed by those who need it. Still thinking about that stuff. So let's just move on today. Right. I've chosen this example because it really does, it was a wake-up call for us at this stage. Really drove home the importance of this. So just to draw your attention to this dip, this was forecasted a day in advance. I handed this actual print to control engineer colleagues. I went into the control room, handed it to them, and said, "Look out for this." And the engineer, I'll never forget, he asked me a very interesting question. He said, "How certain are you that this will actually happen?" So a little bit confounded by this question. I went back to the weather company and asked them, how certain are they about the weather? So they gave me this, and they explained to me the reason that the wind drops down and becomes calm and then picks up again because of this ridge. And you see these isobars, these lines, when they're tightly packed, it means the wind's strong. When they're spaced apart in this region, the wind is less. And then tightly packed isobars to the right. And this whole system would move across, or the forecast said, this whole system would move across Scotland and make the wind calm, just for that period of time, which is, according to this, was about 10 hours. So up till then, never seen anything like this before. So it was really unusual. So went back to the engineer and explained this to him. And he said, "Well, how certain are you that the weather will do exactly that?" So I went back to the weather and they showed me this, which again was an eye-opener. They explained to me that they don't just run one weather forecast about the future. They run 51. And these grey lines you can just about see are individual weather forecasts. But in this case, the wind speed in Glasgow. And the idea being they start each of these 50 weather forecasts with slightly different starting conditions. And they use that to see how these weather forecasts behave as time goes on. Sometimes they spread out, say, all kinds of different wind speeds. And that indicates to them that the weather is very susceptible to those initial conditions. And they use that as a measure of their certainty about the wind speed at that time. Sometimes all of the forecasts stay together and give a very similar result. And they say that they're highly certain about the weather in that situation. So my contact at Meteor Group in this case told me that this dip downwards and then back up with the ensemble spread, as I called it, indicated that there's a high degree of certainty in this particular forecast. So they stopped short of saying you can bet your house on it, but they said they're very certain. So armed with this, I went back to the control room and said, right, definitely going to happen tomorrow. And thankfully, a few days later, I went back, looked through the historical data, and pulled this chart out. And as you can see, 1,000 megawatts is this level. So it went down from about 900 all the way down to 50 megawatts, and then back up to almost 1,000. In the space of about a day, most of the day, about 16 hours, I think, from here to here. So I was quite pleased. Very good forecast. How much time have I got? Right. Okay. Anyway, I'll just have one more minute. Right. What this told me that this is quite serious in a way, because if we imagine nowadays we have in excess of 10 gigawatts of wind farms. So 10 gigawatts down to 1 gigawatt, back up to 10. That's quite a difficult thing to manage. So that really highlighted how important accurate forecasts are for us at National Grid, forecasting wind power outputs. And as the years rolled by, we found that we wondered what would fill in this gap on days like this. And interestingly, someone in the previous presentation today said the Norway fills in this gap. But that's not quite true. What we found is gas-fired generation tends to fill in the gap. So when the wind goes down, the gas-fired power station and demand for gas on the gas network goes up, and vice versa. There's very strong correlation between those two things. And that's something we observed and learned as time went on. So the last thing to mention is probably best to show today's forecast. So I just downloaded today's forecast. You can see that it's developed massively from how it was in 2008. Just take you through some of the features that it has. So just make that full screen. If you just scroll down a little bit. There we go. Right. Okay. So now this white line is the mean forecast. This top level is a little bit small, but that's 9 gigawatts, the upper level. And these blue lines are the level of certainty that we calculate. And we forecast over a much longer period now. This chart shows 5 days. So the current day is this section. Tomorrow, the next day, day after that. But we do gather data, and it's possible for us to forecast up to 10 days in advance. But the accuracy and quality of those forecasts are obviously a lot less. So I think that's where I wanted to stop. Apologies for overrunning slightly. Any questions?
What's your typical error historically?
Typical error. Well, we work out average monthly average error. So, and that's about 5% of the installed capacity. So that's been improving over the years. Back in 2008, if you ask the same question for that, it would be about 25%. So we've improved the system greatly.
Okay, any other questions, observations? I mean, with sort of launch of more satellites and better prediction, how more accurate can you become? Can you project it out to 20 days, a month or something like that?
Well, we're at the mercy of the cutting edge of meteorology. I think that's we're heavily reliant on what the weather forecasters can provide us, because essentially our process is receive a weather forecast and build a wind power forecast on top of that. Yeah. So if the input is not good, then our output's not going to be any better. But I think there is room to improve in the short term by utilising more of our direct measurements to update in the 0 to
6 hours ahead periods.
It's always good to have somebody to blame, though, isn't it? The mess up is
I try not to blame anyone.
okay. Well, time is getting on, so thanks very much for your presentation.
Thank you.